Hello everyone, I am Karthik from ITI section. Today I am going to discuss about the intra-stream synchronization for continuous media streams. Coming to my roll number is 2095191230 and the subject is about the fundamental multimedia. So let us discuss what is this intra-stream synchronization for continuous media streams. In further slides, let us dive into our topic. So, coming to the abstract, the transmission of the real-time streams over best effort networks such as such works has been an interesting research over area for over a decade. An important objective of a research community has been to devise methods that cope the cope with the variations of the network delay, also called delay jitter, that are an inherent characteristic of best effect networks. Jitter destroys the temporal relationship between the periodical transmitted media units that constitute a real-time media stream, thus hindering the comprehension of the stream. Playout adaptation algorithms undertake the labor of the temporal reconstruction of the stream, which is sometimes referred to as the restoration of its intrastream synchronization quality. This paper surveys the work in the area of the playout adaptation, aiming to concisely organize the ideas that have been presented in isolation and identify the main points of difference among different schemes. The survey discusses the issues related to the timing information, the handling of the late media units, the quality evaluation metrics, and the adaptation of changing delay conditions. So, coming to the introduction, continuous media are characterized by well-defined temporal relationship between the subsequent media units. Information is only conveyed with these temporal relationships are preserved at the presentation time. If altered during the transportation, they will need to reconstructed prior to the presentation. The reconstruction of a temporal relationship between the media units of a same stream is referred as an intrastream synchronization. For video presentations, the temporal relationship refers to the spacing or 30 frames per second between the subsequent frames, which is detected by the frame production rate, typically 25 or 30 frames per second. For packet audio, the basic media is a voice sample. The spacing between voice samples is determined by the sampling process. Temporal relationships also exist between a mouse and that belong to the different streams. When these streams are be consumed concurrently, as in a orchestrated audio visual presentation, the lip synchronization problem. The problem of synchronization between the different but related streams is called in interstream synchronization. Issues of internet and the outline. For the assessment of the intrastream synchronization, the quality and several metrics have been proposed. They can roughly be categorized as being of a first or second order. First order metrics quantify how much synchronization loss occurs, and for example expected frequency of gaps, accumulated duration of gaps, etc. In most earlier schedulers designed for packet voice systems, the metrics of a intrastream synchronization quality is the probability or the frequency of a voice packet being discarded. As a consequence of the late arrival due to a large network transfer delay in buffer oriented schedulers, the continuity quality of the stream is affected by the underflow discontinuities. So this is the figure 1 general classification of the playout schedulers. So the playout schedulers are classified into two types, time oriented and the buffer oriented. The time oriented contains the global clock, approximated clock synchronization and no clock synchronization. In buffer oriented we have regulation of MES durations and a pause drop on MES scale. These are the general classification of the playout schedulers. Nearly all presented systems have mechanisms to detect increase The end-to-end latency. Time-oriented systems can tell if a MU is late by comparing its arrival timestamp with its scheduled playout time. Buffer-oriented systems realize a latency increase when they detect an overbuilt queue of MUs waiting to be displayed. The way late MUs are handled divides the proposed schemes into two categories: delay preserving schemes, where all the late frames are discarded to preserve the delay requirements of the stream, and non-delay preserving schemes, where some the late packets are accepted for presentation with the aim to protect the continuity of the stream from further degradation due to the discard of the MUs that have been late. Media type and playout adaptation. Streaming media can be either continuous or semi-continuous. The first category includes the media streams with a regular inter-MU interval, that is R, that is maintained throughout the duration of the presentation. Typical examples are streaming video and streaming audio. Semi-continuous media are characterized by inactivity periods that intervene between the periods of a continuous MU flow. Spoken voice with the silence detection in is a widely used semi-continuous medium. Video programs where the user watches a short video clip and then selects the next one. News repository consisting of consequences of short clips along also belong to the same category. Finally, we note that some schemes are equally appropriate to both continuous video and the continuous audio. Such schemes are those that are decide only the initial amount of buffer data and do not intervene thereafter. Section 4a presents two systems of this category. Also, the simplistic approach of not implementing a digital buffer, section 5a, has been used in both the audio and the video applications. For example, in the VIC M1 tool. Time-oriented playout schedulers. The ideal intra-stream synchronization quality is achieved by completely eliminating any kind of distortion in the temporal relationship of MUs and completely restoring the stream of its initial form. This object must be achieved on the fly as the MUs arrive at the receiver, having crossed a network that alters the spacing between MUs by imposing a variable network transfer delay. The network transfer delay consists of two components, a static propagation delay and the variable queuing delay. Due to variable waiting times in the queues of intermediate network nodes, if the delay variability is unbounded, when meaning that it is infinitely long inter-arrival period may appear, then no scheduler with a finite buffer can eliminate the discontinuities from the reconstruction processes. So coming to the figure, a typical network delay distribution under method 1 of the Naylor and the Callen-Rock, all MUs with the network delay larger than are considered lost. The percentage of the lost packets under the distribution. Here, x-axis is the percentage and the y-axis is the delay. Buffer-oriented playout schedulers. The family of buffer-oriented playout schedulers involves schedulers that delay with the fundamental synchronization latency trade-off, but do not require the time stamping of MUs or the use of clocks. Buffer-oriented schedulers share some resemblance with the time-oriented schedulers that use a differential delay methods to adjust the playout point. Instead of using a timestamps for the assessment of the current level of a delay jitter, buffer-oriented schedulers implicitly uh, assess jitter by observing the occupancy of the playout buffer. Various synchronization latency objectives can be optimized by focusing on the trade-off between the media continuity and the buffering delay. The total end-to-end delay, although known and fluctuating, can be implicitly controlled as a consequence of the regulation of the buffering delay component. The suppression of the buffering delay leads to the suppression of the total end-to-end with a subsequent cost in intrastream synchronization quality. So the figure shows the watermark based playout scheduler of Rothermel and Helbig. The selection of watermarks mainly affects the underflow and the overflow probabilities. The positioning of the target area inside HWM and LWM regularly, the trade-off between the intra-stream synchronization and the stream latency. So coming to the conclusion, this paper has presented in a survey of the literature on playout schedulers. The playout schedulers play an efficient role in the stream communications over best effort networks such as protect the intra-stream synchronization quality of the real-time stream. A significant amount of work has been published in this field, differentiating in a number of key aspects such as the granularity of timing information and the handling of the late media units, the employed metrics, and the adaptation of a changing delay conditions. This paper has tried to provide a structured overview of these issues and taxonomize the proposed playout schemes accordingly. So this is about our topic. Thank you.